All right, so for number 4, ionic or molecular? Ionic, okay, what would we call it? Lithium nitride, exactly. Okay, we write the name of the metal, we write the name of the non-metal. We don't need any Roman numerals or prefixes, lithium nitride. All right, what about number 5? Molecular, okay, and what would we call it? Right, trisulfur dinitride. Okay, and the last one, what would we call that? Okay, it is ionic. What would the name be? Lead 2 nitrate. We would definitely need Roman numerals there because lead can be a 2 or a 4. Okay, 7, ionic or molecular? Ionic, right, potassium is a metal. All right, so we write the formula for potassium, or the symbol, it's a +1. Carbonate, CO3, that's a -2. Drop and swap. A2CO3 for that one. Okay, number 8, iron 2 phosphide. So we write the symbol for iron. What does the 2 tell me?
Not charge.
That's the charge, right? 2+. And as with phosphorus, which is a -3. Drop and swap, we got Fe3P2. All right, and then disulfur trichloride, that's our molecular one, right? So 2 sulfurs, how many chlorines? 3. All right, and then soluble or not? Sodium sulfate. Soluble, yeah. Okay, that's one of those group 1 ion ones. Okay, number 11, silver chloride. Not soluble, yep. Okay, potassium hydroxide? Soluble, that's another group 1. Okay, so that would be soluble. Okay, is that making sense, those ones? Okay, like I said, definitely going to ask things like that again on this week's quiz. Expect some solubility. Less naming this time, but there'll still be a little bit. The reason I keep the naming on for so long is because, as you're going to see today, being able to write formulas correctly and names correctly is crucial for being able to write chemical reactions correctly. Most important, to be able to balance them. That is to make sure that we don't create or destroy matter in the writing of a chemical equation. Okay? Now, another thing that's going to be kind of important for us is to be able to look at a compound like this one and determine how much of each element there is. Okay? In this compound, how many lead atoms are there? Just 1. How many oxygen atoms are there? 6. Yeah. Every nitrate has 3 oxygens, and there's how many nitrates? 2. Okay, so how many nitrogens are there?
2.
Okay, is that making sense? We got to be able to interpret and read numbers. That involves a little bit of multiplication and division. It's all in there, okay? But nothing too stressful. Okay, let's have a look at reactions then. So for today, we want to review, because it should be a review, the signs of a chemical change. Okay? What are some signs that a chemical reaction has occurred? Could get a color change. What else?
Like if it changed from like a solid to a liquid, like the physical.
Yeah, I could get a state change. Okay? It could be a sign, it could also be a sign of a physical change, but it can happen in a chemical reaction. Gas being produced. Okay? 2 ways we might detect a gas being produced. One is visual. The other, smell. Okay? Sometimes you get a chemical reaction and a gas is involved, but you don't see the bubbling and fizzing. It just kind of comes out. And it's because you mix 2 things and then all of a sudden there's a pungent odor. Okay? Sometimes that's the only sign you get. It's just a change in smell. Okay? So could get gas involved, could get smell. What else? Temperature change. Could get hotter or colder. Could be exothermic or endothermic. Okay? Could go either way. What else? We talked about this thing in the solubility lesson that could get formed in a reaction and fall out. A precipitate could be formed. Okay? All right, so that's good. Those are signs of a chemical reaction. What those things indicate is this. what you have after the reaction, that's the products, are chemically different from what you started with. Those are the reactants, okay? But it goes back to Dalton's atomic theory. So if I had, let's say, this reaction here. Let's say I had lead 2 nitrate, and I'm reacting it with potassium iodide. Okay? What will happen in that reaction is I'll get a precipitate. I'll get lead 2 iodide and potassium nitrate. Okay? So obviously what's on this side and this is the products. You might just want to write that reaction and put these little brackets on top just so you know, because I'm going to use those terms all the time. Okay? The products that's produced are chemically different from the reactants. It's made of the same elements, okay, but it's chemically different. So what I wrote there, okay, shows what Dalton said happens in a chemical reaction. Atoms can be separated, they can be joined, and each of those, incidentally, is a type of reaction we'll go over today, or rearranged. This is an example of rearranged. Okay? I still have lead, I still have nitrogen, I still have oxygen, potassium, and iodine. Okay? It's on both sides. I didn't make any new elements. Okay? I just have different chemicals. I have different compounds on the other side. Okay? And this is, of course, why the alchemists thought they'd be able to do things like change lead into gold. Okay? When you start a reaction like this is a clear solution, this is a clear solution. This is a bright yellow powder, and this is a clear solution. Okay? So they mixed two things that were clear, and all of a sudden, pop, there's all this yellow powdery stuff falling out. Okay? They thought they'd made something new. They did. They made lead 2 iodide, but they didn't make any new elements. That's the part they didn't understand. Does that sort of make sense? Now, other thing we have to make sure that we do in a reaction is that we don't create or destroy any matter. Okay? In this reaction, I destroyed and created matter both, according to the way I wrote it. Right? How many nitrates are there on this side? 2. How many on that side? 1. That's a problem. Okay? I just destroyed a nitrate somewhere. Okay? I can't do that. So what I end up doing is I put in what we call a coefficient. We use these to help balance a reaction. Okay, now I have to put a number there to say I have 2 nitrates. I didn't do this. That would have also said I have 2 nitrates, but what would have been wrong with that? Is that how potassium and nitrate go together? Okay, so when I'm kind of messing around with the reaction, I can't change what I have. I can change how much of it I have. So instead of having 1 molecule of potassium nitrate, which wouldn't be balanced, I just said I have 2. Okay, but now I have 2 nitrates on this side and 2 on this side. Why? This 2 also applies to the potassium, doesn't it? So now I have 2 potassium over here. How many are there here? Just 1. Can I put a 2 there? Okay, so I put a 2 there. What did that just do with my iodines? It made it right. Okay? before. I had 2 iodines over there and only 1 over here, but I fixed it. Okay, balancing kind of works that way. We'll work on that a little bit today, but probably it'll be more tomorrow. Okay, where we're just making sure we got the same number of everything on both sides, so we obey the law of conservation of matter. Okay, that matter cannot be created or destroyed. Okay, so that's kind of point number 1. Point number 2, we're going to go over the 5 basic types of chemical reactions. Okay, we're going to learn how to identify each type. Each one is unique. Okay, when you see it, you'll know it's that type just by looking at it. Okay, and lastly, learn how we write them. Well, we kind of talked about that right here. We write the reactants, we write the products. Okay, we drop and swap to make sure they're good, and then we balance the whole reaction out. Okay. All right, any questions so far? All right, so this is what we kind of talked about already. In a chemical reaction, the final products are chemically different than the reactants. Okay, obeying Dalton's 4th point. So, in doing that, is it, in most cases at least, difficult to impossible to go back? Like, if I have a campfire, my reactants are wood and oxygen. Okay, I get fire out of that, and at the end, can I get the firewood back? No, because the firewood has been turned into carbon dioxide and water vapor. We call that smoke. Okay, that's what it is. Okay, but it's gone. I have changed oxygen and wood into carbon dioxide and water. It's magic. Okay, but I can't get the reactants back at that point. That chemical reaction is done. Some reactions are reversible. I can get the reactants back. That's the chemical reaction that powers your phone. Okay? Any rechargeable battery is a chemical reaction that can be reversed through the application of electricity. Okay? We basically just force the electrons to go back to their original position. All right, and then as we said, some of the evidence of a chemical reaction: color change, odor change, state change, energy change, up or down, okay, in terms of temperature. Okay, Dalton's 4th point. Atoms can be separated, joined, or rearranged. We're going to talk joined first. Okay, our first reaction type is synthesis. So here's what I want you to do. I want you to write down synthesis and the definition and these 2 example reactions. But hold on, wait. Don't worry about these letters. Okay, you don't have to include those. Those are the states of matter. We don't worry about those in grade 10. Okay, so just write these reactions, but without that stuff. Okay, I'll give you a few minutes on them. All right, so in a synthesis reaction, we take 2 reactants, usually elements, but they don't have to be, but usually they are, and we combine them to form a single compound. Okay, so that's what we see in the first example. If I take magnesium and I react it with oxygen, I will get magnesium oxide. Right? So basically, I take a dull silvery metal and I leave it out in the air, and I come back the next day, there's going to be kind of a grayish, dusty, kind of grayish black, dusty material on its surface. I'd be able to take it off with my finger and it would end up on my finger. Okay? That's the oxidation. It's like rust, but for magnesium. Okay? If it's rust, it's iron and it turns orange. Okay? But this is the oxidation of magnesium. Okay? So 2 elements combine to form a compound. So you'd have to drop and swap your compound there at the end. Now, is this reaction balanced? Okay, on this side, there's how many magnesium? 2. How many oxygen? 2. Okay, how many magnesium here? 2. And how many oxygen? 2. Okay, so what's the difference between writing magnesium this way and writing oxygen this way? Why didn't I just write it like this? Why didn't I just write 2O? Why did I write O little 2?
Oxygen usually comes in O2. If you put O, it's just basically oxygen.
Right. If you recall, last week, we identified on the periodic table some special elements, the molecular elements. That's the ones that when they're by themselves come as a molecule. Oxygen is one of them, right? We breathe in O2, okay? Nitrogen was another, hydrogen, okay? We had the 7 in the 7 here, okay? And then we had phosphorus and sulfur. This was a 4, this was an 8, and hydrogen was a 2, okay? Those are the molecular elements. If I see a subscript number like this, that's telling me about the structure. Okay? If I see a big number like this, it's telling me the quantity. Okay? So this is saying 2 magnesium atoms. This is saying 1 molecule of oxygen containing 2 oxygen atoms. Totally question. You sure? Okay. Everybody with me on that one? That sort of makes sense? Okay, that's the difference. Little numbers, okay, those have to do with how they go together. In other words, they're bonded together. Whereas a big number just says there's 2 of whatever's behind me, or 3 of whatever's behind me. Okay, we can see that a little bit better here. Okay, if I have a reaction between potassium and bromine, this is 2 atoms of potassium reacting with 1 molecule of bromine, but that is producing 2 molecules of potassium bromide. So synthesis reactions, we're putting the 2 together. Okay. Now, if synthesis is putting them together, taking them apart is decomposition. Okay, when something breaks down, we can say that it's decomposing. So, when atoms are separated, okay, if they are separated, then we're talking about a simple decomposition. We usually just say decomposition reaction. Okay? We are taking a compound and we are breaking it apart. Right? I'll give you a minute or two here to get the definition and the 2 examples written down. Okay, so we can see in both of our example reactions here that we have a compound and it's breaking up into its 2 components. Okay, so this first one here, this is actually how rocket fuel is made. We break oxygen up into hydrogen gas and oxygen gas. Okay, it's actually the opposite of how Mark Watney nearly blew himself up in The Martian. Okay, he was actually trying to put the 2 back together, okay, in order to get water. Right? So this one here just involves the breaking of the 2 apart. Is this reaction balanced? Right? How many hydrogen do I have here? 2 times 2 is 4, right? Do I have 4 here?
Yes.
Okay, how many oxygen here? 2. How many over there?
2.
All right, then we're good, it's balanced. Okay? Making sense? Okay, same thing here with nitrogen triiodide. Okay, if I have 2 nitrogen triiodide molecules, they will break down into a molecule, subscript 2, of nitrogen, and 3 molecules of iodine. Okay, here's the thing that becomes important. Knowing those special elements, because later on we're going to work on predicting the products of a reaction. So all I would give you is this part. You would have to know that when that breaks down, it makes these 2 things, not N plus I, N2 plus I2. They're special. Okay? You have to know when we're dealing with special elements.
Why would you put it as 2I3?
Iodine doesn't go together as 3s. You're right, the number would be the same. It would still be 6 iodine atoms. The number would be right. But iodine is part of the 7 in the 7 that comes at 2. Yeah. It's a good question. Okay, everybody okay with that one? All right. Now, next one we're going to talk about combustion reactions. Not the trickiest reaction, but they do have their own set of rules. They don't work like the other 4. We've only gone over 2 out of the 5 so far. Combustion reactions have their own set of rules. So we'll talk about those as we go over them, okay? So remember, the 7, okay, there's the 7 in the 7, all these yellow ones here. So if you don't have these on your periodic table, these are the ones that come as a 2. Phosphorus is a 4, sulfur's an 8, hydrogen's a 2. Okay, just in case you don't have those identified on your periodic table, those are our molecular elements, or our special elements. Okay, all right. I'm going to give you a minute here to copy down what's on the board there. The stuff about the combustion reactions, okay, as well as the example. And then we'll go over what it all means. So combustion reactions are basically how we release energy from fuel. We've actually shortened the name slightly. We just wrote combustion reactions. It's technically hydrocarbon combustion. Okay? Hydrocarbons are what all of our fuels are. This is a hydrocarbon because it has carbon and hydrogen. Okay? So the stuff we put in our cars, gasoline, that's a hydrocarbon. Okay? This stuff here, hey, anyone know what this stuff is? Comes in little white tanks attached to your barbecue. This is propane. Okay, C3H8 is a hydrocarbon we call propane. Right? Anyone ever fill up a car with gas? Okay, so at the pump, okay, there's different grades of gas, right? There's like regular, mid, and premium. What's the difference? The what?
Well, some of them are like better than other ones.
Better than other ones because they have more what? There's little numbers on them. There's 87, 89, and 91. Starts with an O. Okay, well here's a new one for you then. Okay, that stuff is called octane. Octane is the active ingredient in gasoline. It is C8H18. It is also a hydrocarbon. Which has more energy? Propane or octane?
Octane.
Octane, yeah. There's more bonds in an octane molecule to get broken down. Every one of them that gets broken down releases energy. Okay, you used to be able to convert an internal combustion engine from octane to propane. You just had to carry around propane tanks. Okay, but they lost a lot of power when you did that because propane doesn't release as much energy for the same amount of fuel. Okay, so they wouldn't have as much power. All right, so this would be octane, C8H18. Okay, there's all kinds of other ones. Okay, and we'll go over quite a few of them as we go along. Okay, so the complete combustion or burning of a substance, insufficient oxygen. So combustion reactions are easy to identify. They're always going to start with CH. Okay, C something, H something, and it's going to react with oxygen. We know fire doesn't happen unless there's oxygen. Okay, so a combustion reaction, something is burning. You have to have oxygen for burning. So carbon and hydrogen plus oxygen. Here's the other good news. These two things, it doesn't matter what hydrocarbon you burn, those are the products. Any combustion reaction produces the same two things, carbon dioxide and water. Okay? Usually as a vapor, occasionally as a liquid. Okay? So if you've ever seen on a really cold day, sometimes you'll see water dripping out of the tailpipe of a car. Okay? That's because the water vapor that was produced has been traveling along the exhaust system, but the air is so cold that the water vapor along the edges has actually condensed back into a liquid, and it's just being forced out of the exhaust pipe. Okay? So usually it's a vapor. Okay? It's not often a liquid because usually the temperatures involved will cause it to vaporize. But it doesn't matter which one, even this one. Okay? You burn octane, you get carbon dioxide and water. Always the products. All that changes is how much. The bigger the molecule, the more carbon dioxide and water would be produced as the byproduct. All right, is that reaction, the way it's written, balanced? Okay, well let's check it piece by piece. How many carbon are there here? 3. How many over here?
3.
Okay. How many hydrogen here?
8.
How many over here?
8.
Okay, oxygen's where it gets tricky. Oxygen's in 3 places. It's here and here. When I balance a reaction, I'm only worried about whether the products, all of this, equals the reactants. So how much oxygen here?
10.
Okay, how much oxygen here?
6.
There?
4.
Does that equal 10?
Yes.
Then we're good. 6 plus 4 equals 10, right? Okay, so that reaction is balanced. Here's where combustion reactions go their own way. All the other reactions we look at have the same rule for balancing. Start with the biggest number, balance it, and everything else will fall into place. For combustion reactions, we can't do that. Oxygen will always be the biggest number, and then you have to do it last. Okay, so what I'm gonna do here is I'm gonna write a couple more of these here. Let's just do, so write down these two reactions as I write them down here. Okay, so just write down what I have there. Here, the two reactions and then combustion reaction balancing rules. Okay, and we'll go over those two rules. Let's say I want to balance the top reaction. Okay? The first rule of balancing combustion reactions is that we balance in alphabetical order. That's rule number one. C, then H, then O. Okay, the reason for that is oxygen is in 3 places in the reaction and usually proves to be the trickiest, especially if you don't have enough information to do it with. You kind of have to figure out the rest of the reaction and do oxygen last. All right, so remember, the balancing is just to make sure we obey the law of conservation of matter, that we don't create or destroy anything. Right? So if I'm starting alphabetically and I'm doing the top one here, how many carbon do I have? 5. Okay. How many do I have here?
1.
Okay, so what needs to go in front of this? A 5. It's 5 times 1 is 5. All right, carbons are balanced. How many hydrogen here?
12.
Okay, how many here?
2.
So what needs to go in front of water?
6.
Okay, hydrogens are balanced. Now, I've got numbers in front of both products. Can I figure out how many oxygens there are now? Yes, I can. What's 5 times 2?
10.
Okay, what's 6 times 1?
6.
How many oxygen do I have?
16.
16. What needs to go here?
8.
An 8. Yeah, 8 times 2 is 16. Okay, that's why you have to balance them in alphabetical order. You can't figure out the oxygens until you have done the carbon and the hydrogen. Okay, now that's balanced. Everything is equal. Here, the second reaction is going to demonstrate why we need 2 rules. Okay, let's start this one out and just see what happens with it. Balancing alphabetically. How many carbon?
4.
Okay, so what goes here? 4. Okay, how many hydrogen here?
10.
10. Okay, how many hydrogen here?
2.
What goes here?
5.
Okay, so now if I look at my oxygens, 4 times 2 is
8.
8. 5 times 1 is?
5.
8 plus 5 is 13. What times 2 gives you 13? 6.5, right? Can I have half an oxygen molecule? Okay, so here's why we need a second rule. Okay, now the second rule, because I'm a nerd, I call the rule of 2. Okay, if you're a Star Wars fan, you understand where the rule of 2 comes from. Okay, always 2 there are, a master and an apprentice. Okay, so for this, okay, we have to have a rule that helps us to get past having a decimal in the reaction. Okay, and so you'll never forget it, I will say it like Yoda would. Okay, ready? Okay. If an even number of carbons you have, start your balancing with a 2, you must. Okay, now you'll never forget it, and it's recorded. You can go back and listen to me make a fool of myself over and over again if you want to. Okay, so rule number 2 is the rule of 2. Okay, if there's an even number of carbons, or are an even number of carbons, okay, because multiplying a 0.5 by 2 makes it a whole number, right? Anything 0.5, right? 0.5 times 2, it's 1. 1.5 times 2, it's 3. It always makes a whole number. So if we go back to this reaction, okay, and we get rid of these numbers here, and we start it over, but we start with a 2 instead, I probably won't end up with that decimal problem. Now how many carbons do I have? 8. How many hydrogen do I have? 20. 2 times 10 is 20. So what needs to go here? A 10. Okay. 8 times 2 is how many? I have 16 oxygens here. I have how many here? 10. 16 plus 10 is 26. Suddenly I have a whole number. Okay? That will always work. And you won't forget it because you'll picture me using my Yoda voice in front of my classroom for the rule of 2. Okay? All right. Just in case you didn't get the rule of 2 down there, I'll scroll down so you can see. Okay, once you have the rule of 2 written down, I'll give you about a 3 or 4 minute break here because I've been talking steady and you guys have been listening. Get up, walk around the room, okay? So we have 2 reactions left, but they're what we call replacement reactions. Okay, they're both kind of a similar type. There's single replacement and double replacement. So for the single replacement reactions, okay, you only need to write to here. Don't write anything past replaces it. Okay, don't worry about the example, but do copy down the example equation. Okay. I'll give you a few minutes to get those written. Okay, just to the green mark and then the reaction. So the defining characteristic of replacement reactions is the presence of ionic compounds only. Right? You will never have a replacement reaction where a molecular compound is involved. Okay? So in a single replacement reaction, what you have is an element by itself, and it is reacting with an ionic compound. All that's going to happen is that element that's by itself is going to replace part of the ionic compound. So that means part of the ionic compound will end up now by itself. The big thing with replacement reactions is you always have to produce an ionic compound. Okay? It starts with at least one, and you have to have at least one as a product. For a single replacement reaction, that means the element that's by itself in the reactants has to replace the part of the ionic compound that it is like. So we see in this reaction here that our lone element is a metal. It's copper. And it's reacting with a solution of silver nitrate. When this reaction is done, we now have silver by itself. And copper is now in the ionic compound with nitrate. It bumped the silver out. It replaced the part that it was like. It replaced the metal part of that ionic compound. Okay? So this reaction involves a piece of solid copper in a solution of silver nitrate. And what do I get as a product? Silver. Is that way more valuable than copper? Can you get rich with this reaction? Silver nitrate's really expensive because people can, obviously, it's got silver in it, okay? And you can produce silver from it. But this is actually a pretty simple reaction. Okay? If you were to take like a piece of copper wire, or if you had a penny, okay, or something like that, and you threw it into a solution of silver nitrate and left it there, if you came back the next day, you would have a blue solution. And the penny would be covered in silver. Okay? It would still look like a penny, but it would be silver, not copper. Okay? Now, I don't mean the whole penny is silver. This is a process we call plating, or electroplating. It means a replacement reaction between metals where the new metal plates out on the surface. Okay? So if you took the penny out, you'd be able to like flake the silver off in little tiny flakes, okay, from there, and then there'd be copper underneath. You can put it back in and the reaction would continue. Okay? But we know a reaction has happened because the penny looks different and the solution turned blue because copper containing compounds are blue. Okay? It's an interesting reaction when you see it happen. Okay? We actually use reactions like this for lots of things. One of them, okay, used to be used for this, for rust proofing. Okay? You used to buy a car, and if you wanted it rust proof, they would electroplate the bottom with zinc. Okay? It's cheap, okay? But it would plate out and it would oxidize and sacrifice itself for the steel. As long as there was any zinc on any part of the frame of the car, none of the iron would rust, okay? Because it would react with the zinc first. But it was an electroplating reaction that would get the zinc on there, okay? All right, so does everyone kind of follow how that worked? Okay, what happens is the element replaces the part that it's like. So it could also go like this example. Okay, I could have this, so I'll have you guys write this one down because it's similar. Actually, do this instead. Let's get that produced to something. Okay, does this follow that same pattern? Okay, this time that lone element was a non-metal. When the reaction happened, it replaced the non-metal part of the ionic compound. Now nitrogen is off by itself and chlorine is now with magnesium. Okay, making sense? So single replacement element replaces the part of the ionic compound that it's like. That's all that really happens. Is that reaction balanced? Okay, so let's look at the balancing rules for everything except combustion reactions. Okay, here's the rule. Start with the biggest number. What's the biggest number in here?
Magnesium.
Magnesium, it's a 3, right? How many magnesium here?
3.
Okay, how many here?
1.
1, so what needs to go here?
3.
Okay, when I put that 3 there, how many chlorine does it give me?
6.
Okay, what needs to go here? Okay, is it balanced now? Yes, there's 2 nitrogens on both sides. Okay, that will work. Like, there would be the odd time where, oh, shoot, that didn't work. Then you start with a different number and it'll work the next time. Okay, but like 98, 99% of the time, biggest number, that'll work. You'll get it balanced the first time. Okay, so sometimes people like to have like a bit of an analogy to remember this. Don't be insulted by this. Chemistry is old-fashioned. Okay, the analogy is a little old-fashioned. Okay, so the analogy is this. You always have to produce an ionic compound. So that's metal, non-metal. So let's imagine that this dude is a metal. Metal, non-metal. Okay, well, he replaces the dude. Okay, and so the other dude ends up by himself, and this guy ends up with the girl. Okay, now, I don't get 2 dudes together in that reaction, okay? Because chemistry is old-fashioned, okay? There's nothing wrong with 2 dudes together, okay? You do you gotta, be who you are, okay? But chemistry is old-fashioned. You can't make an ionic compound that way. 2 metals never bond to each other. That never happens. Metals do not chemically go together. So you never have, like, Be2, Okay, hydrogen does because it's an exception. Okay, but like none of the other ones do. All right. Now, also, if two non-metals went together, I wouldn't have an ionic compound. I'd have a molecular compound. So remember, you always have to produce an ionic compound. That's why they use this analogy. I'm not going to say it's a great analogy. It's pretty old-fashioned. Okay? Questions on that? Okay. Last reaction type. Double replacement. I'll give you a minute to write that down, okay, as well as the example, and then we'll talk about it. So, double replacement reaction works very much like a single replacement, except instead of an element, you now just have two ionic compounds. Okay? The two ionic compounds are going to react, and the only way to get two ionic compounds on the other side is if the metals switch partners. Okay, so basically that's all that happens in a double replacement reaction. The metals switch partners, and then I still have metal, non-metal on the other side. Okay? So in this one, calcium is with chlorine. In the reactants, sodium is with carbonate. Okay, but in the products, now calcium is with carbonate and sodium is with chlorine. They've just switched partners. That's it. Okay? These reactions, okay, oftentimes you'll get a precipitate formed out of these. Okay, precipitate's that solid that's not soluble, okay, and falls out of solution. All right. Is this reaction balanced, by the way? Okay. How many calcium here? How many on the other side? How many carbonate here?
3, 2, 1.
That gets people. Polyatomic ions always throw people in these kind of reactions. Okay, carbonate is CO3. There is one CO3 here, and there's one CO3 on the other side. Okay, 2 chlorines. How many over here? 2 sodiums. 2 sodiums. So we're good. Okay, here's another one. I want you guys to write this one down. Okay, so we got lead 2 nitrate, and it's reacting with potassium iodide. And that is going to make lead 2 iodide and potassium nitrate. Okay, when you have that reaction down, remembering that we start with the biggest number to balance, see if you can balance that reaction. Okay, I'll give you a minute or two to try to balance it, and then we'll balance it together, and we'll talk about the one other thing we want to be able to do with a reaction like that. All right, so according to our rules, we start with the biggest number. Biggest number is 2. Okay, there's 2 nitrates, there's 2 iodines. Let's start with nitrate just because it's on this side. I've got 2 nitrates here. How many nitrates over here?
1.
Just 1. Okay. So do I put brackets in a 2 or do I put a 2 in front? 2 in front. I can't change what the compound is. I can change how much there is. When I put a 2 there, though, it also means I have 2 potassiums. So what needs to go here?
2.
Okay. When I put a 2 there, does it fix my iodine on the other side?
Yes.
Always a good sign. Okay? If you're balancing one thing and as a result of balancing that, something else works out, you're on the right track. This is now balanced. Okay? There's 1 lead, 2 iodines, 2 iodines, 2 potassium, 2 potassium. Okay? 2 nitrates, 2 nitrates. We're good. All right, last thing I want you to be able to tell me. One of those products is a precipitate. Which one? Check your solubility check. That's how you do it, right? One of those is a precipitate. The lead 2 iodide is the precipitate. Okay? Potassium nitrate is soluble. Lead 2 iodide is not. That is exactly the kind of thing I would ask in a multiple choice question that combines 2 concepts, replacement reactions and solubility. Okay, here's a reaction. Which of the products, if any, is soluble, right? And then I could have, you know, option A, lead 2 iodide, B, lead or potassium nitrate, C, both, D, neither. Okay, and you have to pick. Okay, I think for today we'll stop there. Tomorrow we're going to work more on reactions. Okay, remember, labs are due on Wednesday. Okay, I had a ton of people come in and have them looked over. Okay, I can look over them tomorrow, scheduled help and lunch, and after school. Okay, I can't do after school today, but okay, I can look over those 2 times tomorrow. Can't do it in the morning, we've got a staff meeting in the morning, so if you come here, I shan't be here. Okay? All right.